afternoon. I will talk about our work. We spent the last 5 or so years self-assembling metal structures from nanoparticles using DNA origami technique, and I will mostly focus on the structures which can be controlled with external stimuli. So we heavily rely in our work on DNA origami technique, so this is a method which allows you to build complex, self-assembled nanostructures completely out of DNA. So you can build 2-dimensional, 3-dimensional, curved or polymerized structures simply by self-assembly. Typical dimension here is in the order of hundreds nanometers. The way the technique works, you take a long single-stranded DNA, usually comes from a virus, and then a bunch of synthetic shock DNA pieces, which are designed to bind 2 distinct places of this long guy, and then fold it together in the desired shape. For example, a smiley face. So everything happens in a solution, so you mix your stuff, you put some salt, you heat it up, as you cool it down, it assembles. That's how a smiley looks under AFM. Diameter is around 100 nanometers. Excuse me. Well, an interesting feature of this technique is that each of the short DNA pieces inside the structure is unique in its sequencing position, so you can functionalize it with some chemical modification, which then will act as a binding sites for assembly of other materials, like proteins, quantum dots, metal nanoparticles, and so on and so forth. And so, for example, here there are 26 proteins assembled with a resolution of around 6 nanometers. So it could be a technique that allows you to build complex structures with desired properties and hopefully functionalities, and you can also implement the stimuli response into your systems. It proved to be rather useful in the field of nanophotonics. Just to give you a few examples, so we use this technique to build 3-dimensional plasmonic structures, which show a strong circular dichroism in the visible range. Philip Tennerfield group in Braunschweig showed that you can use it to build optical antennas and position an emitter directly into the gap of the antennas. This is, of course, in connections for field-enhanced properties like fluorescence or surface-enhanced Raman scattering and so on. And recently, Paul Rosamond in Caltech uses small origami structures to position defined number of emitters inside an optical cavities. So now you can imagine if you want to put, let's say, a single fluorophore inside a cavity, it's a nightmare. But if you use a DNA origami, you can do it rather easily. Okay, so I will mostly talk about structures like this. So they consist of 2 gold nanorods assembled on an origami template, which is around 80 nanometer long here. So these 2 rods, they make a high-wall structure, which shows a strong circular dichroism response in the visible range. And if you manage to change the angle between the rods, you can change the response of the structures. And we actually implemented several ways how you can control the geometry of these guys using DNA hybridization, light, but I will mostly talk about pH approach to switching. So since I come from the field of DNA nanotechnology, for us, when we think about dynamic structures, the natural way to do it is not so simple, but it's based on the Toehold-mediated strain displacement reactions. So basically, to keep the story short, what it allows you to do is to control the state of different DNA sequences. For example, you start with blue and red in the duplex state and green in a single-stranded state, and then you end up with a green and blue in a double-stranded state and red, which is in a single-stranded state. So we took this approach, we modified our DNA origami structures with these locks, which can be switched into the closed and open state just by pipetting correctly, carefully designed DNA strands into a system. So just to show you how it looks under TM, so these are our DNA origami templates. This is the 2 rods assembled on them. With the rods, they prefer to land like this on the TM grid. Yeah, and importantly, the structure does switch, so you can switch it between left-handed configuration, right-handed configuration, or let's say undefined angle configuration. So that's what we actually see. So when we pipette the correct strands into the system, it goes to the switching in the optical activity response. So yeah, this is basically a very large molecular switch with around 10 megadaltons molecular weight. It's a plasmonic system which is controlled now with external chemical stimuli. and it's a structure which couples its geometry to a plasmonic response. Well, there is one problem that if you cycle it, you can see the performance decreases, and the reason is here. So it's a chemical fuel, and when you power your system with chemical fuel, there is a waste, and your system simply degrades with time. So a solution for it is to use something which is waste-free, like light. That's kind of an obvious continuation. We took the very well-known light-switchable molecule azobenzene. So it can exist in two photoisomeric states, cis or trans, and depending on the state, it can either stabilize or destabilize DNA duplex. So then we took the azobenzene switches, plugged it into our origami templates, and use a light to switch the configuration. So again, assembly happens with a nice yields. And yes, you can switch the structure now back and forth without any decrease in performance multiple times. Yeah, now the structure is a bit faster than the previous one. So kinetic, so the switching happens in the range of minutes instead of tenths of minutes, and it follows a standard first-order chemical reaction kinetics. Well, so now it has all these benefits. In addition, now you can switch it multiple times, and with using light, you can get high spatial and temporal resolution. So you can excite structures in the place where you want, when you want. And yeah, it's remotely controlled. You don't need to pipette anything into your system. Well, and this is our most recent work. So we actually moved from DNA duplexes to DNA triplexes. So everybody probably knows that there is this Watson-Crick base pairing between CG, AT, but there is actually another way you can form not just duplexes, but triplexes. So for example, the T base can come from a site and form TAT triplex, or a protonated C base can come from a site and forms CG C triplex. So it's so-called parallel Hookean interactions. So you have 3 strands, and the design rule is that for TA in this guy, there is another T or C on the third guy. Excuse me. Well, important feature here is that formation of the triplexes is pH dependent. So if TAT forms in the pH range below 10, but CG and protonated C forms at pH range only below 6. The reason is that you actually need to protonate your C to form this triplex. So we now design our triplex strands. We can switch them by pH. We plug them in our origami structures. And, well, again, assembly is good. CD response is very strong. But importantly, we can now tune the range of pH in which the structure switches simply by tuning the content of TAT triplex inside your switch. OK. And well, another important feature is that switching is now much more faster because it's only limited by the speed of protonation, deprotonation of your bases. So it happens in the order of seconds instead of minutes. And then you can start to play around with your system. You can design different structures which will have response in the different pH range. So the structures, let's say you can have a right-handed one and left-handed one. They are quasi-enantiomers in the sense that they are almost the same. The difference is just in 2 or 3 bases between them. Right? And then you can, OK, if you take 2 of these guys, you can now form a system which will be optically active only in the very narrow range. So you start with the guys which are all, let's say, closed. Since they are enantiomers, they cancel each other. Then when you increase pH, one of them going to open, so you get an increase of your amplitude. And then when you increase pH more, the other guy will going to open it, again, cancel each other. OK, and if you have 4 guys, then you can build this kind of strange responses that they are optically active in 2 pH ranges, or it's, let's say, left-handed in this range, but right-handed in that range. OK. So yeah, now it's actually very simple to implement the stimuli response, and you can also selectively control different population of structures inside your mixtures. Yeah, just to conclude, now we can build complex self-assembled structures using DNA self-assembly. We can control them with a number of external stimuli. Depending on what you want to do, each one has some advantages and disadvantages. There is another way, which is based on shape complementarity, introduced by Henry Lee's lab 2 years ago. Okay, so I have to thank all the collaborators who helped me to do this work. So all the switches were actually built in the NALIU lab in Max Planck Institute in Stuttgart. We collaborated with Tim Liedel in LMU, Sasha Govorov in Ohio. Other benzene strands were provided by Musiaki Endo in Kyoto, and Francesco Ricci helped us to build these pH-sensitive triplexes. So yeah, thank you for your attention.
Thank you. Yeah, I don't know if you need the mic, maybe just...
So I was wondering, if you have this light-induced change here of your DNA, so why is it so slow? This was still in the range of several seconds to do this? Because the normal transition in the molecule is pretty fast.
Yeah. Yes, exactly. But it depends on the intensity of your light source.
So right? It's the interaction of the light, you don't have enough.
Well, so the way it was done is just with a pocket flashlight. Right, so I take a pocket flashlight and a filter, and that's my excitation. Yeah. It's very weak. So right, if I would take something more powerful, it's going to be faster.
Would it be not a strategy to use exactly this kind of plasmonic structures also to enhance, maybe to catch the light or enhance this kind of interaction that you get the light there, to have a larger scattering cross-section?
I'm not sure.
They should make it faster, right?
Yeah, maybe. Yeah, but I mean, I didn't want to push the speed aspect. I was just very happy that I could do it reversibly, through many cycles. That was my main concern.
Hey, thanks for a nice talk. So you showed these dimer switches in solution, but if you were able to actually fix them onto a substrate, say the bottom one on the substrate and the top one could still stay rotating, could you do this in like say a single metamolecule system or a single plasmon particle?
Yes, the question is then how can I detect it?
Also optically, like say either through single particle white light scattering or...
we always use a CD, which is a straightforward way to detect configurational changes. So I'm not sure if I have even a monolay of my structures, if they're going to give me enough response. So this is something I want to do, because surface gives you a lot of flexibility, or exchange of your reactors and blah, 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 blah.
Yep.
But not yet.
Okay, great, thanks.
Yeah, we might have time for a quick question. No? If not, Andrea, I think you're the next one on the list. And we should thanks again Anton for his presentation. Thank you very much.